In this video, we're going to examine an expanding universe. We're going to be looking at the Big Bang Theory, mainly the work of Albert Einstein, and examining early ideas about the universe. So here's Albert. He developed his special theory of relativity, which was a new way to look at the universe. He proposed there was a space-time continuum in which time can slow down. Objects shrink if they're going fast enough. Nothing can exceed the speed of light. We predicted that if you try to accelerate an object to the speed of light, some of the energy you put into it is converted into more mass, making it bigger and harder to accelerate and therefore impossible to reach the speed of light. He deduced the relationship between energy and mass, E equals mc squared. He believed that mass and energy were different forms of the same entity. However, this was inconsistent with Newton's law of universal gravitation, where the gravity between two celestial objects depended on mass of objects and the distance between them only. He eventually published the general theory of relativity. Some interesting facts about Einstein. He wasn't very keen on wearing socks. Galileo Galilei was Albert Einstein's favourite scientist. He didn't really talk until he was about 3 years old. Apparently, the first words he spoke were, "This soup is too hot." And the family, surprised at him speaking, said, "Albert, why have you never spoken before?" He said, "I didn't really need to before now." He continued to be a slow learner and spoke very slowly as a child. One of the famous quotes about Albert Einstein is, "Insanity is doing the same thing over and over again and expecting a different result." He loved to play the violin and continued to play until just before his death. Apparently, the pathologist who made Einstein's body's autopsy stole his brain and kept it in a jar for 20 years, and his eyeballs are in a safe somewhere in America to this day. Einstein also failed his university entrance exam and had to reapply a year later. He worked as a clerk in a patent office during that time. Albert Einstein proposed his theory of relativity in 1915. This was a new way to look at the fabric of the universe, a space-time continuum in which time can slow down and objects shrink. With this in mind, Einstein also deduced his famous relationship, E equals mc squared, and from this he believed that mass and energy were simply different forms of the same thing. The mathematical model involving gravity, space and time as a fourth dimension, gravity the result of the warp or curvature in space-time continuum. Since large masses have the ability to warp space-time continuum, then perhaps planets are not travelling in a curved path, but rather following a straight path through curved space-time. So what does this ability of large objects mean? Well, let's have a look at the case of our own sun. The mass of the sun causes space-time to curve, as can be seen here. So freely moving objects, such as planets and comets, follow the straightest path possible allowed by the curvature. And we can see this with this comet here. Circles that were evenly spaced in flat space-time become more widely spaced near the central mass. Now, of course, the theory of relativity contradicted Einstein's own belief that the universe was static. So what he did to overcome this was introduce a cosmological constant, and this overcame the notion that the universe was expanding and ensured that it was static as he believed. Alexander Friedmann, 1888 to 1925. He omitted Einstein's constant and found that solutions supported the notion of an expanding universe. This made two assumptions. The universe looks identical whichever direction you look, and this is true whatever your viewpoint in the universe is. There are three different types of expanding universe models that satisfy Friedman's assumptions. The first is the closed universe. Mutual gravitation of matter in the universe is able to bring expansion to a halt and pull all matter back together, causing it to contract. The flat universe. Expansion is just fast enough to balance out the force of gravity. Expansion slows but never quite stops. And the open universe. The universe is expanding so fast that gravity can never stop it. Some additional theory. Pulsating universes. Some scientists theorize that another Big Bang will occur, leading to a pulsating universe. Let's take a minute to review some units of distance. We're familiar with the metre, the fundamental unit of length in the metric system, and we know that a kilometre is equal to 1,000 metres. However, we may have come across the astronomical unit before, but may not necessarily be too familiar with what it is. It's the most commonly used unit of distance in the solar system. It's equal to the average Earth-Sun distance, or approximately that very large number of kilometres here. I'll leave you to work out how many that is exactly. The next unit that we'll look at is the light year. And we're familiar with the fact that it is equal to the length travelled by light in 1 year, and is equal to this very large distance here. Try writing that one down in words. The parsec, the preferred unit by astronomers outside the solar system, is defined as the distance at which one astronomical unit subtends an angle of 1 second of an arc. That's 1/3600th of a degree. Well, the distance an object has to be for its parallax to equal 1 second of an arc, equal to 3.26 light years, or the largest distance of all, which is this one here. Then, of course, when we start to move beyond the solar system and look at distant galaxies, we're going to be talking about kiloparsecs and megaparsecs. Now this brings us to Edwin Hubble, who lived between 1889 and 1953. You've probably heard of the Hubble Space Telescope. Well, Edwin Hubble didn't invent that, but it was simply named after him as he was such a renowned astronomer. So he studied nebulae, and nebulae are clouds of glowing gas and are the birthplaces of stars. He was able to see images of individual stars in the nebulae, and he found pulsating stars which are so predictable that their distance can be easily calculated. He showed that the star was in a different galaxy altogether, and this was the first evidence of galaxies other than our own. He eventually discovered and classified 24 different galaxies. Now, one of the things he did do was measure the redshift of light of newly discovered galaxies. And when light is spread into a spectrum, particular lines at specific wavelengths are able to be identified. He noticed that these lines were closer to the red end of the spectrum than to be expected, hence the term redshift. And he deduced that this meant they were moving away from the Earth, and was now able to calculate how fast they were moving based on the degree of redshift. We see here the spectral lines on a distant galaxy up at the top are shifted towards the red end in comparison to a medium distance galaxy, a close galaxy, and a close star, where we see there is virtually no shift in the spectra whatsoever. He published his results in 1929, which showed that nearly all galaxies were redshifted, moving away from us, and discovered a direct relationship between the distance of the galaxy and its apparent speed. The further away equaled faster, and this is known as Hubble's law. And we can see Hubble's law described here by velocity of recession, how far it's moving away, is equal to Hubble's constant, which is 70 kilometers per megaparsec, and the distance from us measured in megaparsecs. Since things which are furthest away are moving faster, This really implies that at some stage all the matter in the expanding universe was once concentrated in a single place, a singularity. Of course, then came the Big Bang, and we picture this as a massive explosion outwards from that singularity. Now, we've already seen that redshift is evidence for an expanding universe. Now, we've also got cosmic background radiation. So scientists were searching for cooled radiation left over from the young universe, and it suggested that it would appear as microwaves from space and could be searched for. It was inadvertently found by a telescope which was tracking communication satellites in 1965. Many experiments were conducted following this discovery. Let's have a look at COBE. In 1989, a new satellite was launched called Cosmic Background Explorer, or COBE, which accurately mapped the strength of the radiation. So what have COBE's results been? Well, it's managed to plot the age of the universe at about 13.7 billion years old. The geometry of the universe is flat. The content of the universe, 4% atoms, 23% cold dark matter, 73% dark energy. The formation of the first stars were about 200 million years after the Big Bang. Well, that's all we're looking at in an expanding universe. In the next video, we'll be looking at Big Bang theory and what happened immediately after the Big Bang and in the years following up to the formation of our solar system, including the Earth.